Alright, we're going to talk about applications of trig functions. Let's take a look at this next slide. When you're solving right triangles, first you want to begin by drawing out the triangle and then labeling the given information. And then depending on what we're looking for, we're going to use sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So let's take a look at an example. Okay, so here we have two examples, example A and then example B. Notice that we're only given one angle. That's because we know it's a right triangle. So when I draw my triangle, let's label this A, B, and C. So angle B is 32 degrees. And we know angle C is 90 degrees, therefore angle A is going to be the difference of that. And that difference I'm getting from 180 degrees is in a triangle, so therefore 180 minus 90 degrees for angle C minus 32 degrees for angle B, I get 58 degrees for angle A. We're also told that side C is 12. And now we just need to find, so far to the list we can add that we solved for A equals 58 degrees, and we're missing side A, which is opposite angle A, and we're missing side B, which is opposite angle B. So in order to find those, I'm going to set up a trig function. Let's start with cosine, and we'll use angle B, which is 32 degrees. So cosine of 32 degrees equals adjacent over hypotenuse. So cosine 32 degrees equals adjacent over the hypotenuse. And notice that we're in degree form, and now we need to use our calculator, multiply both sides by 12. 12 cosine 32 degrees, put that into your calculator, and we get A. Right. After we put that in our calculator, let's round our answers to 2 decimal places. And we get A is approximately 10.18. And what we want to do is we want to do the same thing in order to find B. But because I have side A, I have side C, I have an option for Pythagorean theorem. Or I can continue using side angle 32 degrees opposite B equals hypotenuse 12, which is sine. I'm going to choose that option. Again, you can use a Pythagorean theorem at this time. So here we want to do the sine of 32 degrees equals opposite over hypotenuse. I'm going to multiply both sides by 12. And I'm going to put that into my calculator and round to 2 place values. And I get 6.36. So that's how we solve for a triangle. We find all the missing angles and any missing sides. So let's try B. Let's set up our triangle. If I want to, I could put angle A down here, B here. Remember, typically you put C for the hypotenuse, so C goes here at the right angle. Side A is 13.5. Remember, it goes opposite of the angle. And notice that B is in degrees and minutes. I'm going to convert that to decimals. When I divide 18 by 60, I get 0.3. So angle A is 60.3 degrees. And I'm going to start with the sine of 60.3 degrees. Opposite is 13.5, and the hypotenuse is C is what we're going to start looking for. So that's the sine of 60.3 equals opposite over hypotenuse. This time when I cross multiply, basically I'm just going to flip-flop this, put this over 1, and it's going to be C equals 13.5 divided by the sine of 60.3. We're going to put that into our calculators, and we are in degrees again. And we get that C to two place values is approximately 15.54. The next thing we want to do is find angle B. I could have done this before I found side C. And I know a triangle is 180 degrees, so I'm going to do 180 minus 90. That's 90 between these two angles. Minus 60.3. Angle B is 29.7 degrees. And now I'm just missing side B. So if I want to, I can use the Pythagorean theorem now that I have C and A and find B. Or I can use my trig functions again. I can either use angle B or angle A. For consistency, I'm just going to use angle A. You don't have to pick this one. So cosine of 60.3 equals adjacent over the hypotenuse, which we just found to be 15.54. I'm going to multiply both sides by 15.54. And then I'm going to round to two place values. And I get 7.70. And that's how you solve a triangle. So again, what you want to do is you want to find all the angles in the triangle and all the sides of the triangle. All right, example 2 says find the altitude of this isosceles triangle, round to two place values. We're giving theta. Remember, in an isosceles triangle, these two angles are equal. And we're given side B. And when I drop an altitude, this side is bisected, meaning 12 is going to be divided in half for this part of the triangle and this part of the triangle. So let's do that. Let's draw an altitude. So now I know that this portion is 6. This is still 32 degrees. And we're only interested on this side. So now let's think of the trig function that incorporates this angle with opposite over adjacent. And that's going to be tangent. So we have the tangent of 32 degrees. Make sure your calculator's in degree mode. Equals opposite, let's call it the altitude A, over adjacent 6. Multiply both sides by 6. And now we can find side A. All right, let's round to two place values. A is approximately 3.75. Now let's switch it up a little bit and we're going to look at some word problems. What you want to do is you always want to start by setting up a diagram or drawing a picture and then solving with any of the trig functions we've been talking about. Let's take a look at this example. Here we don't have to draw a picture, they're providing one for us. It says find the height of the tower given that is 150 feet from the line of sight. So here's a person standing in the line of sight of the individual who's looking up at the top of the tower at a 60-degree angle. So we want to find the height of the tower. So if I have this is 60, that's opposite, that's adjacent. So now I know my trig function. Tan of 60 degrees equals opposite over adjacent. Make sure you're in degree mode. We're going to multiply both sides by 150. And then we're going to round A to two place values. Actually, I'm going to round to the nearest foot. So A is approximately 260 feet. If you rounded to two place values, that would be 259.81. Right, this next one we still have a picture drawn for us, which is very nice. The length of a kite string is 30 feet when the kite is 10 feet above the ground. So this length is 30 feet when this height is 10 feet. So notice that the kite string, that's not going to alternate, but depending on the wind, this might be reduced. What is the distance between the person flying the kite and the point immediately below the kite? So we're looking for B. Here, this is just the Pythagorean theorem. So we have 10 squared plus B squared equals C squared. That's going to be 100 plus B squared equals 900. Subtract 100 from both sides. Take the square root of both sides. I'm only going to take the positive solution because we're talking about distance. B is approximately, and let's round that to about 2 place values, 28.28 feet. And this, if I wanted an exact value, would be 20 root 2, but because I want to know the length, let's approximate it to maybe 1/100 of a foot. All right, example 5, we have a hot air balloon is ascending with you in the balloon as a friend is filming your ride. The friend is 50 feet away from where the balloon took off. When your friend first starts filming your ride, her camera is at a 30-degree angle. And we see that right here. After a minute, her camera is at a 70-degree angle, and that's right here. How far did you travel in that minute? What is the speed in feet per minute? So what this problem is asking us is, after being right here, how far is this distance? So what we need to do is solve 2 right triangles, this little one and this bigger one. I'm going to find A, I'm going to find B, and I'm going to take the difference, and that's how far she traveled in 1 minute. So let's first start with the little triangle that's in the bottom right here. So if I'm interested in side A, that's going to be the tangent of 30 equals opposite over adjacent. Multiply both sides by 50. And let's round A to 2 place values. All right, I get 28.87 feet. And now I want to find the bigger triangle. So here I have degree 70, opposite is B, and adjacent is 50. So let's set that triangle up. That trig function, tan of 70 degrees equals opposite over adjacent. So again, multiply both sides by 50. Put this into your calculator. Remember, we're in degree mode because I see the degree symbol. And round to 2 place values. Okay, that's 137.37 feet. This is her total distance in that time frame from when her friend started recording, but I want to know how far she traveled in a minute. So what I'm going to do is I'm going to take B, and I'm going to subtract A. All right, in 1 minute, your friend traveled 108.57 feet. All right, now let's talk about bearings. Bearings are interesting, okay? All right, well, in navigation and surveying problems, the term bearing is used to specify the location of one point relative to another. The bearing from point O to P in these diagrams is the acute angle. Notice that all of these are acute angles. Okay? Measured in degrees, always in degrees, between ray OP, remember this is a ray, and a north-south line. Here's our north-south line in all of these diagrams. The north-south line and the east-west line are always going to intersect at 90-degree angles. Each bearing is going to have 3 parts. Okay, let's take a look over here. This is a bearing. A letter, north or south, which would be here, north, north. This one's south. And then we're going to have the measure of an acute angle. So here we have 40, 65, 70. And then we're going to have east or west. Okay, so if an acute angle is measured from the north side of the north-south line, like this one and this one, we always put north first. We want to indicate, is it on the top half of the coordinate plane or is it on the bottom half? So when I'm writing bearings, I'm either going to indicate north or south first. Then I want to incorporate the angle. The angle always comes out from the north-south line. Okay, it's always acute, whether it's going to the right, to the left. So let's say I was northwest 40 degrees. That would look like this. So this one is pictured north 40 degrees west. And then we're going to incorporate the east-west line. So am I on the right side of the coordinate plane? That's east. Or am I on the left side? That's west. So if we look over here, north 65 degrees west, remember it always has to come out from our north-south line. This one's south, 70 degrees east. Never draw your bearings coming from the east-west line. We always do them north-south, and then we go either towards the east, towards the west. And the same thing down here. All right, so what is the bearing from O to B? Here we have O to B. So we're looking for this angle. I'm going to go ahead and fill in some angles so we can solve these together. All right, so I went ahead and I put imaginary values for these angles. And we're interested on bearing from O to B. That's this one. So again, we always look at our north-south line first. This one's clearly on the north side, so the first thing I want to do is indicate that it's on the north side. Your angles always come out from that north-south line, and it goes in this direction. So that's going towards the west at 40 degrees. So we write north, 40 degrees, west. All right, next one we have, what is the bearing from O to C? Okay, so let's take a look at that one. That one's interesting. The bearing from O to C. O is the origin here to C. Remember, we always indicate this north-south line first. So it's really this angle here. So in this diagram, we're getting tricked by the 75-degree angle. I really need to do 90 minus 75 to get this coming from the south line. So I'm going to do 90 minus 75 is 15 degrees. And remember, that's our bearing coming in that direction. So we're on the south side of the north-south line. We're going towards the west at 15 degrees. So that's the answer for part B. Our next one says, what is the bearing from O to D? That one's not that bad because we don't have to solve the difference of the angle. Here, we're just going in this direction, O to D. Remember, O, origin to D, and we're going in this direction. We're on the south side of our north-south line. Our angle coming out from the south line is 25 degrees, and this time we're going towards the east, here in this direction. Okay, if I was looking for O to A, don't make the mistake of saying it's 20 degrees. Remember, it always has to come from the north and then go towards the east. So 90 minus 20 is 70 degrees. This bearing will be north because we're on the north side of our north-south line. 70 degrees east. All right, let's take a look at this example. Example 7 says a sailboat leaves the entrance to a harbor and travels 30 miles on a bearing of north 40 degrees east. The captain then turns the boat 90 degrees clockwise and travels 20 miles on a bearing south 50 degrees east. At that time, how far is the boat from the harbor entrance? And what is the bearing of the boat from the harbor entrance? So let's pretend there's no diagram and let's just draw this from scratch. So this is going to be my harbor entrance. Then I'm going to do an imaginary north, south, east, west axis. And I know that my bearing, I'm going north 40 degrees east to start. So going northeast 40 degrees, and we go at that distance for 30 miles. Then we turn 90 degrees clockwise. Now we're going in this direction, 90 degrees, but they tell us, if it helps you, do another north-south line here, that we're going south 50 degrees east. So this angle in here needs to be 50, but overall I know that this angle is a right angle. Okay, so now my boat is over here. And the question is, how far is that boat from the harbor? We're looking for the hypotenuse. And don't forget that we traveled 20 miles. So we're looking for C. We have a right triangle. This is a squared, b squared. We're looking for c squared. So let's go ahead and solve that. So this is how you would do it if no diagram was given to you. Do it one point at a time. Draw a bearing, go that distance. When the bearing switches, draw that distance, and then put the rest in context. So we have 30 squared plus 20 squared equals c squared. Alright, so we have 30 squared is 900, 20 squared is 400, c is equal to the square root of that. Let's round that to two place values. I get 36.06 miles. That's how far out that boat is. Now the second part, what it's asking you is, if someone were to leave this harbor and you were stranded out here, what bearing do they need to take in order to come rescue you? So we're looking for the complete bearing from here to here in order to go find you. So we're looking for that angle. So if it helps you, put theta in this diagram here. This is the angle we're looking at. But remember, bearings run from north to east. So when I find theta, that's not my answer. I have to add it to my initial bearing where I left at in order for the person to leave the harbor at that angle and come find me. So in order to find theta first, that's step one, I'm going to use my trig functions. I have opposite over adjacent. If I wanted to, I can also use the hypotenuse, which I just found. So tan of theta equals opposite over adjacent. Or we can write this as inverse tan. Theta is equal to inverse tan 20 over 30, or 2/3. Put that into your calculator in degrees, because bearings is always in degrees. And let's round. Alright, rounding to one place value, I'm getting theta equals 33.7 degrees. But remember, we're talking about bearings. So the person needs to leave 30, this is 33.7. Whoever's coming to rescue me needs to leave at this bearing. And then they'll be able to go on this direction and find me. So that's north, because we're on our north side of our north south pole. And then I'm going to do 40 plus 33.7 is 73.7 degrees, and I'm heading east. And that's the bearing we're looking for. Must be in degrees. Alright, trig functions are really good models for things that are going to occur again and again. So for instance, if we're talking about a vibrating guitar string, or a swinging of a pendulum, or a bobbing of an object, Or even in this diagram, we have this ball, pretending this is rope attached over here to this wall. Okay, and if I pull on this rope, it's going to go up and down, up and down. So it's going to repeat. So when we're talking about something that looks like that, like the ball will continue bobbing up and down, and then this spring, these up and down oscillations are called simple harmonic motion. Okay, if we look over here, D is representing our resting position. Our D is the displacement, the how far up, how far down it's going. You can think of it like the amplitude when we were just exploring our trig functions on the actual XY axis when we had to graph them in the test we just took. Over time, that distance, if we look over distance, is going to get shorter and shorter. Okay, it's going to keep going up and down, and that's going to alternate until eventually it comes back to rest. So when we're talking about these curves, our simple harmonic motion, an object that moves on a coordinate axis, is in simple harmonic motion if its distance from the origin D at the time t is given by either we have our cosine or our sine curve. The difference in these two is where it begins at rest. If it, at time 0, it begins here in the position of rest at d equals 0, that's our sine curve. Think about the origin being the point of start for the parent graph. If it starts at displacement, or I'm holding the ball over here, or I'm pulling it way down here, then that's going to be my cosine curve. The amplitude is still the absolute value of A, and my period, remember we were defining it as 2 pi over B, but because we're talking about simple harmonic motion, we're going to switch that B to omega, where it has to be greater than 0. A period gives the time it takes for the motion to go through one complete cycle, because eventually it's going to come back to its rest state. The frequency, let's call that F, equals 1 over the period. Again, you can think of the period as 2 pi over B, but here we're using omega. Look at an example. It says a ball on a spring is pulled down 5 inches below its level when it is at rest. So this tells me I'm starting 5 inches below its rest position. That's the cosine curve. So if I were graphing this, here's 5 inches below, and I pulled the ball down at rest. I'm holding the ball over here. So because I start at displacement, I know that I have to use cosine. I meant to write D. T equals cosine omega t. Okay, the period of the motion is 3 seconds. So they're giving me the period, and they want me to write the equation for the simple harmonic motion. Well, if I'm starting it below, I already have what my amplitude needs to be. It needs to be -5 cosine. And now we just need to use the formula for period to find, remember that's 2 pi over omega, to find what W is. So I'm going to manipulate that 2 pi over omega equals 3. Multiply W on both sides, and then divide by 3, and we get omega equals 2 pi over 3. So now I can substitute that in here, 2 pi over 3, and then we're expressing t because that's part of the formula. So this is my equation. And now we want to find the frequency. Remember, the frequency is F equals 1 over the period. Remember, the frequency is the reciprocal of the period. Okay, it's the number of complete cycles per unit time. And what I'm going to do is I'm going to take the period, 3 seconds. So therefore, the frequency is 1/3 of a second.